In this video, I'm going to talk about the idea of coordinate vectors. So I'm going to start with my standard set of axes here in R2. And my standard basis for R2 is 1, 0, 0, 1, and this corresponds to the axes. So for instance, if I wanted to do the vector 2, 3, right here, I know I would need 2 times 1, 0 plus 3 times 0, 1 to get me 2, 3. So it tells me how far I need to go along my x-axis and how far up I need to go along my y-axis to get to the point. However, what if instead I wanted a different set of axes? I had a different basis. And now, instead of that vector, I want to look at this one here that comes down. So how can I describe this? In this particular case, I went down 2 on this vector. So I would have a 2 and minus 3 on this vector. So this would be 2, negative 3, but it's not the same 2, negative 3 as I have on my standard graph. So the idea is, if we have a different basis for R2, we're essentially changing our axes. A new basis gives a different set of axes for the coordinate plane. So I want to look at how to deal with these different axes in my coordinate system. I'm going to start with the idea of the unique representation theorem. Let's suppose I have a basis for my vector space V given by this B1 through Bn. Then we know that every vector x in my vector space V can be written uniquely as a linear combination. So I have C1, B1 plus C2, B2 all the way up to C and Bn. We know we can do this for every vector and that it's unique. The fact that we can do this for every vector comes from the fact that the basis must span the vector space. So that tells me that every vector can be written as a linear combination. The fact that it can be written uniquely comes from the fact that a basis is also linearly independent, which tells me that not only does this exist, but it is unique. Let's suppose that we have a basis B1 through Bn for V, and we denote it by this script B. Let's also suppose x is a vector in V, and we know by my unique representation theorem that x can be written as a linear combination of the b's. The coordinate vector of x relative to b, we can then define, we write this as my vector x with a subscript of b. And this is the vector given by C1, C2 up to Cn, so the coefficients of this linear combination here. Here I have B1 and B2 to form my basis for R2. And I have a coordinate vector x sub b of 5, negative 2, and I want to find the value for x. So what I said was that x of b, in this case, since we're dealing with R2, this would be equal to C1, C2, where x is equal to C1, B1 plus C2, B2. Sticking in what we have for this particular problem, we know x of b is equal to 5, negative 2. We don't know x. C1 is equal to 5, so I have 5 times b1. C2 is negative 2, so minus 2 times b2. And now from here, we can easily find my value for x. This is 5 plus 2 is 7, and 5 minus 4 is 1. So now I have my value of x. This time I have a basis for my given vector space. I know x is this vector negative 2, 22, minus 16, and I want to find x of b. So what I'm looking for is x of b. Since I have two vectors, this will be equal to C1, C2. where x is equal to C1B1 plus C2B2. Plugging in what we know, we don't know what x is, that's what we're trying to find, or we don't know x of b is, that's what we're trying to find. We don't know C1 and C2. We do know what x is. X is -2, 22, minus 16. I don't know what C1 is, but I do know what B1 is. It's -4, 2, minus 2. And then I don't know C2, but I do know B2. -3, -2, 1. And we can see that this right here is the same as just a system of equations. So I'm going to set this up in a matrix. We would have -4, -3, and then on the right of the augmented column, -2. The second row would be a 2, a -2, and a 22. And then a -2, 1, and -16. We then need to work on row reducing this, and I won't go all through the steps, but we get 1, 0, 0 for the first column. The second column is 0, 1, 0. And then to the right, I have 5, -6, 0. So my coordinate vector, x of b, is going to be equal to the solution here, which is 5, -6.